You're all set, Rachel. Pablo.
Okay, thank you. Hi, everybody. My name is Rachel Sibley. I am the QE test lead for the Red Hat in-vehicle operating system initiative here at Red Hat. I also have Pablo Martin joining me, and he's been primarily working on the designing and enablement work for our code coverage workflows. So today, I want to cover a brief overview of what is Red Hat in-vehicle operating system, high-level test activities for qualifying ASIL-B packages, how we're rerunning upstream test suites here at Red Hat and in Rivos, the evidence traceability, trying to tie together requirements to executed runs, and code coverage techniques. So a brief recap of what is the Red Hat in-vehicle operating system and what is this initiative here at Red Hat. We're working on developing an operating system, a version of RHEL, a slimmed down version of RHEL that is specifically designed for in-vehicle application workloads. We're working on becoming certified, both initially and continuously certified. Our requirements are primarily driven by both our customer engagements and functional safety requirements. We are working on designing a smaller set of the operating system and identifying parts of the operating system that are in the ASIL-B scope. For the most part, all of the RPMs packages that we're inheriting are from RHEL. We're not going to rebuild them, they'll be inherited except for the kernel. This is the only package right now that we're working on that will be rebuilt. So our high-level test activities for quality engineering is rerunning existing RHEL tests. We need to adapt them to an OS3 environment. The tests were primarily developed to run in a traditional RPM compose. So there are some differences with running in an OS3 environment to get them to run there. We're also working on migrating them to our test management tool. This is a test framework that we use within Red Hat for quality engineering, and we run it both downstream and within our upstream layers. Sorry, I'm already losing my voice. We're working on enabling automated code coverage workflows for the packages in the ASIL-B scope, designing new test coverage based on our safety requirements, and then working on our evidence traceability. We'll be storing our test cases, requirements, and executed runs in Polarian, which will be used for our test case management system. So many of the tests that we're inheriting from RHEL, they run at different levels. So unit level, integration level, system level, for example. We also have something called reverse dependency testing that we want to inherit from RHEL that we plan to rerun for Rivos. The naming is a bit confusing, but essentially it's part of our gating process where we're working on blocking changes that might interfere with promoting a build. So components, depending on other packages, could be negatively affected by changes in their dependencies. So this can be configured by updating a YAML. It does test up to 2 layers of dependencies. So we can, by default, it will test up to 50 dependencies, but we can identify those specific dependencies that we'd like to retrigger based on the YAML file. And of course, this depends on the packages that we're targeting for both the OS3 TMT test management tool migration. So the tests have to be written in a standard way to be able to take advantage of this. So we at Red Hat obviously strive to open source as many tests as we can and contribute there. So we have many open source tests for all of the packages in the operating system. This is an example of what we have for kernel. and are used and fetched by our kernel CI system. So we have tests in the CentOS stream repository under kernel tests. These are all of our open source kernel tests that are used to test in something called CKI, continuous kernel integration, which is responsible for gating our and promoting our both the patches and the builds downstream, also heavy engagement with upstream layers. We also rerun many upstream test suites, not only test suites that are part of the source RPM, but also other related upstream test suites for a specific package. So this is just an example of some of the kernel upstream tests that we wrap and rerun downstream for RHEL. So for the Red Hat in-vehicle operating system, it's important to us to also take these same upstream test suites that are rerun downstream and rerun them for Red Hat in-vehicle operating system. And again, all of these tests are located in our CentOS stream repository under kernel tests, if you're interested. We also test upstream kernels. So for kernel CI, CKI will work with whichever maintainers from the various subsystems, Linux trees, whichever maintainers will allow us to test their kernels. We will take a recent commit, build a kernel and test it in our infrastructure, and then send a report running our tests. So this is just an example of a report that was sent. We also have tests that we actively contribute in open source in CentOS stream CI, and also for Fedora dist-git. We do have to have the tests written in the standard way, the test management tool, and this is also an open source test framework. So for evidence traceability, we are working with RHEL quality engineering. We have a working group that includes folks from RHEL QE and also from the Red Hat in-vehicle initiative, where we are working together to define all of these requirements needed for traceability. So we will be taking existing RHEL requirements, legacy requirements, and mirroring them in our test case management system, Polarian, including, and this we'll also be pulling in new safety requirements or functional safety requirements needed for the automotive initiative. Those will be embedded within our test case management system, where we'll derive test cases and link our results in, so that everything will be tied together and traceable in a manner that we can have it all tied together. We're also looking into using something called Report Portal. This is something I'll talk about in the next slide, but it's used for automatic triaging and taking test failures and making sure that they're tagged to an existing issue, whether it's a test issue, a product bug, or an infrastructure issue. This is just an example of what the requirements would look like in our test case management system, Polarian. We'll have some partial bidirectional traceability, where we'll be able to tie the requirement that's in Polarian to the requirement that's in Jira. And then we can have these synced on and agreed upon schedule. And this will allow us to generate traceability reports so that we can understand if there are any requirements that are missing test coverage. I mentioned Report Portal. So we have Report Portal plus the test failure analysis classifier. This is something that uses machine learning and AI to automatically tag failures with known issues. So it was developed by both Red Hat and IBM. There is still some human intervention to be able to train it and to be able to confirm its accuracy. So we are working on defining requirements to understand if this is something that will be able to work for our needs. So This is taken from the ISO 26262, and this is speaking about the importance of the completeness of the verification of to provide the evidence for testing our requirements, and the different techniques that are used at both the software unit level and also the architectural level. The recommended techniques, whether statement, branch, decision coverage for the unit level, highly recommended or recommended, and then also the function and call coverage for the software architectural level. So for the automotive initiative, we are trying to target the 100% code coverage for the packages in the ASIL-B scope. Now I know that is can be difficult to achieve, especially for kernel, which I'll talk about in the next slide. But what we are attempting to do is working on running the code coverage against the package source repo for all of the existing coverage, including the new test coverage. We'll be designing and automating for requirements-based tests. We'll generate reports that will cover specific metrics, including branch, statement, function, and additional ones that Pablo will talk about later. We're working on running the code coverage using our test framework and in an OS tree environment. And we're also trying to shift left and encourage our upstream, which is RHEL, to also begin using this within their CI infrastructure. So we're working on automating these code coverage workflows, tying them into CI. This will allow us to identify if there's any gaps and then increase the coverage to an acceptable threshold. So what if we can't reach that 100%, which is more than likely with kernel? We want to investigate specific options that we can target code coverage for paths that would either interfere or support safety requirements. There's also possibility of splitting it into separate parts for QM and NSR code, where we can assign the code coverage target to the ASIL-B part. What we'd have to ensure that we have the FFI between the two parts of the package, freedom from interference. Additionally, our safety claim is integrated with reliability figures with RHEL, so this would be part of our justification. So at this part, I'm going to hand off to Pablo, and he's going to speak about the work he's been doing with the enablement and design work for code coverage.
Okay, thank you, Rachel. This is Pablo Martin, quality engineer from Red Hat. I work with Rachel and a great team on the Red Hat in-vehicle operating system, initially on performance testing and now on functional safety, which is the area that covers this kind of code coverage and this effort for fulfilling the requirements in ISO 26262 for ASIL-B. I will present some options that we researched, the one we choose, and how we are using it in our toolchain. First, the Red Hat in-vehicle operating system differs a bit from other embedded systems that may have had to pass the ASIL-B certification. It is a fully fledged Linux system, having modules and packages coming from heterogeneous sources with the different development goals and schedules, and most importantly, the different build systems that they may have. So adding code coverage to them is a bit different than it may be when targeting a single application or an embedded system that is built from a single set of sources where there is only one build system involved. First, we are going to talk about static instrumentation, the traditional option, which is GCOB. It is part of GCC. GCOB works by instrumenting each of the object files being compiled, inserting into them routines that for each source code line insert a stub that updates a counter. That counter keeps track of the number of times that line has been hit. This means that the resulting code has a performance penalty in the end. This has to be taken on account for non-functional tests that measure performance. But the idea is that any instrumentation doesn't modify the functional tests that are being run. So the same test with and without coverage must have or yield the same results. This is specified on the standard specifically. It says if instrumented code is used to determine the degree of structural coverage, it can be necessary to provide evidence that the instrumentation has no effect on the test results. This can be done by repeating representative test case with non-instrumented code. So we are covering this because the same tests that are being done for functional testing, the different packages are the ones that are then run with code coverage. The instrumented binary does not have a special runtime requirements. This is especially important in our case or in the case for a whole system because we are modifying the building of the packages or rebuilding them. We are taking the packages and adding them the options to have code coverage, but on runtime, after installing them, there is no other thing to do. So we can use the system as it is, let it boot with the default options and all the rest, and code coverage for the enabled packages will be retrieved automatically. Imagine that if we have a daemon, a good example is systemd. Having to run something in parallel to systemd will complicate things. This is especially important when we talk of dynamic instrumentation. For dynamic instrumentation, the most used example or the most used program is dyninst, named aptly. It implements runtime code instrumentation, so the binary doesn't need to be recompiled. This is a big advantage, for example, for an application that doesn't have to be rebuilt at all. You get the same binary, but then you need to do something when you run it alongside that binary. There is another process, the patcher, that in runtime, all these stubs of code that updates the counters are then uploaded in memory. So the running binary, the running program is patched. Then again, as I explained with Jacob, this is a big question for us for libraries, for example, because then any user of the library needs for any use of the library for any program that is depending on the library, we would have to run this patcher program alongside it. This is in contrast to GCOP, where you just recompile the library, and any user of the library will then have code coverage enabled. Okay, Rachel, if we can go to the next slide, please. Thank you. Based on hardware virtualization, and again with no instrumentation, it is Coverture. Coverture is based on QEMU, so it cannot run on the final hardware. This is important if the requirement is to run the tests on the final hardware, which is the case for Red Hat in-vehicle operating system, especially for the kernel and other packages. It is very experimental at this phase, but nonetheless very interesting because it has the good things of both the options that we saw before. It doesn't require compiling, and also it doesn't require anything to be set up on the on booting the program that is, or on launching the program that is going to be covered, because all the statistics are retrieved from the outside of this virtualized environment based on QEMU. There are also commercial tools. I mentioned here Squish Coco because it is very used. It's also based on binary instrumentation, and this means that the build system needs to be modified, but the modifications for it are more specific because it's not just taking an option already existing in GCC, but changing the binary or adding a wrapper alongside the binary for the compiler. This complicates things for cross-compiling and things like this. Also, I know that it has a very polished results analysis and IDE. Okay, can we go to the next slide, please? Thank you. Then specifically for GCOP, because we are using GCOP, there are different frontends. Different GCOP displays coverage information in text format. And then there are tools that with the GCOP output produce an HTML report or file suitable for other frontends. So we have LCOP, which is the traditional frontend. It is written in Perl as part of the Linux test project. Supports lines, function, and branches coverage. GCOP is retrieving data for every line and every single token that is being hit or not. But then the frontend needs also to keep counts of those. So not all the frontends have the same information. Then we have GCover. GCover started at 2012 as a more flexible LCOP, specifically to have support for other frontends, such as Cobertura using Java testing, SonarQube, coveralls. So these generate the XML files or the JSON files needed to upload the code coverage info to those systems. It is more modular and easily modifiable than LCOP. Currently supports decision coverage. The current version, earliest one didn't, but this one supports decision coverage, which is one of the structural coverage metrics that needs to be met by ASIL-B. And code coverage has been developed as part of this effort. And currently the pull request for it is queued for merge. So if you go to the GCover GitHub project, you could see the pull request for call coverage being queued. Yeah, later on, I will elaborate a bit on why call coverage is important. Can we go to the next slide, please? Thank you. So, this gets specific on our toolchain with details for RPM packages. They can be of use also for any other package system that comprise the upstream sources and a set of patches, and also a build system. In this diagram, I marked in red the build products that go to the testing environment itself, and in blue, the products that will be used to generate the report. So we start from the left, from the upstream source files, and the .spec file specific to RPM packages, and the patches themselves to the upstream. These all are parts of the source RPM package. And as Rachel mentioned, we are not modifying the Red Hat Enterprise Linux packages, but the kernel. So these are the same versions and the same source RPM packages as for Red Hat Enterprise Linux for the user space programs. Then we get a modified spec and the coverage packages. We add our own patch to the build process to have the options for code coverage. And then we call the regular RPM build that then calls autotools, CMake, depending on the package, the build system that is being used. And we get the modifier RPM and the GCNO files. In the GCOB system, GCNO files are the files that contain the information that links the binary object file with the actual lines in the source that they refer to. So it is the static information that is retrieved on build. And then another product is the patches source files. These files are also needed on the report because the report will show line by line each of the source files and which lines were hit, which ones wasn't, and the rest. So if we go to the next slide, please. Thank you. On top, there is the machine that will perform the tests. And it gets the modified RPM package. Installation happens with RPM OS 3, which is a different approach than on regular Red Hat. OS 3 is a system of a layer file system to optimize for flash memory and also to have snapshots of the system. This is a bit different. So the installation happens with RPM OS 3, and the product is the binaries that are modified from this RPM. The version of the RPM would be the same, but then we overwrite the binaries from this one. Then we run within the testing framework. We use TMT. TMT is an open source product led by Red Hat that we use to perform the tests. They run a coordinate testing plan, and in the end, there is the functional result, the same that we have to get without code coverage, and then the GCDA files. These GCDA files on green are the ones that will be used to generate the report afterwards. So these are the ones generated at runtime. The GCNO were the ones at build time, and the GCDA are the ones that we need to retrieve at runtime. So if we go to the next slide, please. Thank you. And then we generate the report. This slide shows how to generate the report with LCOB. With LCOB, we first get the GCDA files and the .cnh files, the source files, and generate the coverage.info, which is an intermediate format used by LCOB. And with that, we generate the HTML. The importance of the intermediate format is that we can merge test results coming from different runs, different sets of tests. They can come from different machines as long as the packages that were installed were the same. And then they can be merged, so all the statistics, or whether a line has been hit or not, or how many times, will be merged in the end on the final report. If we go to the next slide, please. Again, with gcover, it's a bit different because the intermediate format is the JSON format. So for this, we'll have to modify also a bit this pull request because it's only generating HTML output. But for having the ability to merge, we need also to have the JSON format with call coverage. In this case, there are no two different tools, but gcover at first generating the JSON, and then gcover with this option add trace file that performs the merging from other runs or from other testing systems. In our case, for example, the tests for the kernel can come from both from testing farm and from CKI. So we also needed a way to merge the results coming from those different systems. in yellow here, I am coloring the intermediate files that can be used for merging the different test runs. So if we can go to the next slide, please. Here is the index output for a run on LCOP specifically for the ACL package. I choose this because it has a small number of lines. And here we can see line coverage and function coverage provided by default by LCOP. And if we go to the next slide, thank you. We see the HTML report from Gcover for an example file that I wanted to use to showcase the call coverage and decision coverage. So we can see here when for this file, for this example file, that we have on the left columns with the branches being covered or not. The branches are numbered by Gcov just with numbers, but from left to right, so we can identify which one is being taken or not. If we go specifically to the line 36, where there is a branch taken and a branch not taken, we see one of two. So we see that the branch not taken is the one that enters within the if, and the one taken is the one that doesn't, because C is 0 always. So we see in red the statements that had not been hit. Those doesn't have a specific column, but a specific color. So in red are the lines that are not covered. And if we look at decision, again, here decisions being taken or not are the same as branches, one of two. And within it, in the call column, we can see that there are 0 of 2 calls taken in line 38. This is because there are 2 functions within that line. None of them has been called. And there is one function in the one after, also not being called. So on the top right, we can see the summary of lines, functions, branch decisions, and calls being executed, and the percentage that they represent within the file in this case. For the listing, we could see an overall stat for the whole project. And regarding call coverage, that wasn't in the cover before, or what does it add to a statement or function coverage? We have to take into account that code coverage does not guarantee that every possible value for any variable is tested. That would explode geometrically in time and effort for any non-trivial case. So when 100% of coverage is not reached, the different stats can be helpful to identify parts of the code that need more testing. So if a function covered by function coverage appears in the function as hit, it means that it has been called once, or at least once. But then call coverage can show that there are another 100 of calls that have been not covered. Just by looking into the statement coverage, we cannot infer which of those pertain to calls or not. So this is if we go to 100% statement coverage, of course, we have 100% call coverage for that module. But when we don't, this helps us characterize whether a certain function is not well represented in a test. If there are many calls for that function not exercised, it shows that many use cases for it in the code are not covered. So more testing for hitting specifically that function would be needed. That's something that without call coverage could pass without knowing. So if we go to the next slide, please. Thank you. Okay, here it is a screenshot of GitLab in action. We use GitLab for CI, so all the intermediate artifacts are stored and tagged. This provides a cache, allowing us to quickly assert if a new test provides more coverage, as the build files do not need to be recompiled. These GCNO files that come from building can be stored, and as long as we don't change the version of the package, which would require a rebuild, we are reducing all the time in the tool chain from these artifacts being stored, those GCNO files. That makes it very fast to know whether a new test that has been added apports or adds more coverage or not. Even this is something that could be done, sorry, with the merging, that previous runs can be stored, and only the statistics for the new tests are run. So only the new tests is run. Okay, thank you for attending. I hope you find this useful, and any question, of course, any suggestion is welcome.
I see there was a question in chat, and yeah, thank you, Gabrielle, for answering already. But the question was, does Red Hat plan to qualify all these tools per needs of ISO 26262? And yeah, as Gab mentioned, yes, this will be part of the tool qualification. We're currently actively identifying all of the tools we use for RHEL, and Rivos will be taking a subset of these tools as we're inheriting a lot of the testing and techniques that RHEL is already doing, and those will be pulled into the tool qualification. Were there any other questions besides the one that was asked in chat? The next question is, the coverage measurement happens usually in the unit test phase, which is the lowest level testing. Are these Rivos packages also undergone requirements-based testing? Are these requirements for these packages as well? So yes, when we speak of an RPM as a unit, since we have thousands and thousands of RPMs, and the RHEL operating system, Rivos, will be a subset of that. But when we refer to a unit, we are essentially referring to a package. So I know unit has different terminology depending on how you refer to it. But right now we're working on code coverage for the entire source RPM, but additionally we are going to look into running code coverage as well for the merge request level or patch level as well. And this will be tied to the requirements-based test that would be tied into that. Next question, are you thinking also focus on 62304 as ELISA additional work group? I don't have an answer for that. Maybe.
So, Rachel, can you hear me?
Yes.
Yes. Now, so when you say 62, I mean, I have another question for Andres, if I pronounce your name correctly. When you say 62304, you mean the medical standard, I guess,
yes,
right?
exactly. Because two work groups in the ELISA are automotive based and also medical. So right. I would suppose there will be some focus also to medical.
Right. So yes. So we need to, I mean, distinguish between ELISA and the Red Hat in Vehicle OS operating system. They are complete. I mean, Red Hat in Vehicle OS is a proprietary operating system from Red Hat. So ELISA is a Linux Foundation project that, you know, is meant to to be active on multiple domains, including the medical domain. So from an ELISA point of view, the answer is yes, indeed. Okay, so effectively the idea is to provide techniques and ingredients that can be used, widely, including also, the medical domain. Yes.
Okay, thank you, Gab, for answering that. And then the next question was, how do you prove FFI between the packages?
Yeah, if I may answer, it is a great question. FFI, as any other call to a library, can be tested as part of the target library. So for example, if a package is calling a function of glibc, we can get the glibc RPM that has code coverage installed, and then run this test that is testing this user space program that we know that is calling this specific function of glibc, and we will retrieve the code coverage after the call, and we will know which function was covered in the library. Can we go back and know which line was been calling it? No, or not at this point, but yeah, it is a great question.
Is there any traceability between the test case's specification and the safety analysis failure modes? So yeah, this will be handled as part of the requirements. We'll have requirements that will identify safety based on safety analysis. They'll be inputted into requirements, which will be in JIRA, which will then design our test cases to show that we're showing that traceability between the requirements to the safety analysis. Next question, there's also the tool impact and tool failure detection ratings, which impact tool confidence levels as part of ISO 26262 Part 8. Not all used tools need to fulfill all of ISO. Okay, this is more of a statement. Yeah, I think this will come as when we get to the tool qualification part as part of our FUSA certification. Okay, Pablo, maybe you want to handle the next one. Are you looking at execution code coverage, which could include aspects like preemption, parallel execution beyond source code coverage?
Not that I know at this point. We are focusing on the stats that are required for ASIL-B, but as part of the non-functional testing, those are also interesting. Also, in the case of parallel execution and preemption, the non-reproducibility issues that may arise, or how to get always the same results in those environments. But yeah, those go beyond the current scope.
Is code coverage information collected throughout the CI process or only for releases? Did you want to answer that, Pablo, or do you want me to?
Yes, okay. It is not only for releases. It is on when pull requests are requested because they take the testing with code coverage takes more time than without it. But yeah, it is in a continuous manner, but not in the same schedule as the regular testing that happens for each commit. I think, Rachel, you can.
Yeah, so for the package level testing, we generally will trigger off of updated builds, RPMs, and run our non-coverage testing. Code coverage is time consuming and expensive, especially if you're taking kernel code coverage and then merging all the reports together. That can take a long time. So we're not going to run it every single time there's an updated build. But we're going to run it periodically at a predefined cadence. And then we'll additionally, as we're working on enabling more techniques like at the merge request level, that's where we'll run it more frequently based on changes or patch level basis. Yeah, if the coverage test reveals holes in the packages, example given dead code, unreachable code, does such a result have impact on the package, i.e. lead to code change of the package? I would think so. We haven't traditionally run code coverage formally within Red Hat. We've run it mostly for only a few packages, primarily kernel, and it wasn't run at a regular cadence. So with Rivos working on functional safety, we're really trying to change the mindset across the organization and within RHEL, so that we'll start running this as on a regular cadence to be able to identify dead code, unreachable code, to be able to improve not only our test coverage, but also the actual the source code for a given package. So for Red Hat and Vehicle Operating System, ARM. And then x86 for development purposes, but officially supporting ARM. A lot of good questions so far. Thank you. Are there other questions anyone wanted to ask?
I don't see any other questions in the chat. We give folks one more minute. Anyone else has anything?
Yeah, I do see one more question. Sorry, I was muted. Any plans for supporting MCDC coverage required for ASIL-D in the future? And I know we are primarily targeting the ones recommended, highly recommended for ASIL-B. But I know we're looking at other techniques, such as I know Pablo was looking at the call coverage, the function coverage, and the decision coverage as well, to see if we could pull in more of these techniques for our certification. So yes, the more we can pull into these reports, the better.
Yes, specifically there is a question on whether the decision coverage in the GCOV equals the MD DC coverage. There are some projects arguing that they reach 100% MDMC coverage as SQLite, and SQLite argues that for the C programming language, they are equivalent. And they argue that because you know that in C, when the order of evaluation is such in a condition, if there is one of the conditions that is true and there is an OR after, then the rest is not evaluated. And also happens with an AND when it is 0 from left to right. So they argue that both are equivalent for the C programming language. It would be different for other languages and other embedded languages for which MDMC was targeted. But yes, there is an ongoing research on that also. Yes, there are no tools that I know of that support MDMC open source tools as it is defined.
Does the testing involve also the kernel as a guest in a VM? Not at this time. We're mainly targeting our reference platform at the moment, but that could be in scope later on. And then somebody, oh, that was Pablo posted the SQLite link. Do we know if GCOV produces the data required to calculate MCDC and we need to update GCOVR, LCOV, or does GCC GCOV need to be enhanced to generate MCDC coverage?
That's a great question. I don't know. If GCOV needs to be modified, GCOV itself, then it is a very different effort than modifying a frontend like GCover. If the data is there, then it's just a matter of storing the stats and counting them. But if it is not, then part of GCC itself will need to be modified. I don't know.
Right. Yeah, we're just trying to pull in as much as we can, but yeah, it's not a requirement for ASIL-B. Are there any other questions? We have 6 minutes left. Okay, I think we may be done, unless more lingering questions come in. But feel free to reach us outside of this presentation for more questions. Thank you again for joining. Yeah, I appreciate all the great questions and conversation.